Hello, and welcome to the video lecture for Chapter 4, Part 1. In this video, we are going to mostly focus on talking about the sun and why seasons occur. But before we get into that, I wanted to do an application of something that we covered in the last video. In the last video, we wrapped it up by talking about the law of gravity and the laws of motion. And there's an application we can do where we can utilize those laws to understand why a particular effect occurs. And that effect is called the tides. When you think of the tides, what do you think of? For a lot of people, the ocean levels changing, how high or low the ocean levels can be, is an effect that we call the tides. And you might notice this when you go to the beach, if you are there for an extended period of time, several hours, that where the waves crash on the beach can vary over the course of those hours. This is a gravitational effect between the Earth and the Moon. Now, if you remember the law of gravity, it is an inverse square law. So there's a distance dependence on the law of gravity. Now, in the picture here, they show the Earth and the Moon is off to the right-hand side. The Moon, on average, is about 384,000 kilometers away. The Earth's diameter is just under 13,000 kilometers. Now, that 13,000 kilometers is a significant amount of distance compared to the distance to the Moon. And what that means is the right side of the Earth, as seen in this picture, has a greater gravitational attraction to the Moon than the left side does. It's like about a 3% difference or so. And what that does is it causes what we refer to as a differential gravitational effect. The right side is being pulled harder than the left side. Now, when we sort of balance these forces relative to the center of the Earth, it has the effect of sort of squeezing the Earth, or imagine pulling the Earth on both sides to kind of create like a bulge in the Earth. And it doesn't have a major effect on the actual landmass of the Earth, but approximately 70% of the Earth is a fluid and can easily move. And what happens is this sort of tugging that occurs causes the water to pool up on certain areas of the Earth and then recede from areas that are not in the direction of where that pull is located. And this is precisely why sea levels can rise and fall, because the water is pooling up on those areas. Now, the tides, because of Earth's rotation, are going to alternate every 6 hours. As you see in the picture at the bottom here, we see that the Pacific Ocean next to the Americas is experiencing a high tide now, and looks like the Indian Ocean on the other side is experiencing a high tide. So the ocean levels are going to be a little bit higher over there. As a result of that, it's going to recede from where we can see where the South Pacific Ocean is and the Atlantic Ocean is. This is the first order effect of the tides. This is the main reason why they occur. It's this differential gravitational pulling that occurs that causes this. Now, the sun produces tides as well. Not quite as strong. They're about half as strong. And what this means is that the sun and the moon can act in tandem to produce either enhanced or diminished tides. So in the picture in the upper left here, we see the full and the new moon. So whether the moon is full or new, what happens is Earth, moon, and sun all line up. And so the moon and the sun are sort of working together to produce a stronger than normal tide. And we call that spring tides. It's an enhanced tide. So that would mean like the ocean levels can vary a lot more because of that. The picture at the bottom is what's called a neaptide. And that's when the moon and the sun kind of act against each other to produce a diminished tide. So the moon pulls in one direction and the sun pulls in a perpendicular direction. Now, it doesn't cancel the effects out because, again, the sun has a weaker effect, but it does act to produce diminished tides. We call those neaptides. And this is a second order effect. We'd say it's a it causes tides, but it's not the main reason why the tides are occurring. There are lesser order effects as well, precisely where we are in our orbit and where the moon is in its orbit. It's going to determine exactly how lined up things get. And so there's some other minor effects, but these are the sort of the main reasons why this is occurring. This is pretty natural for moon planet systems. And sometimes this can be very extreme. For example, when you look at a couple of the moons of Jupiter, the inner ones, one's called Io and one is called Europa. Io is a really interesting example. If you look at a picture of Io, it's spelled I-O. You can just look up Io Jupiter, like in Google or something. And when you see a picture of that moon, you see a lot of like patchiness on the surface. A lot of the features that are on Io are volcanoes. And they are caused because Jupiter produces tides on Io that are so extreme that the inside of Io sort of gets melted and produces all this volcanic activity that occurs. Europa has a similar situation. Europa is more of an ice world. That's opposed to like a fire world, like Io is. And there are these massive fissures that you can see on Europa, and that's caused by cracking. And a lot of those cracks are due to tidal effects. So this could be really extreme in some circumstances. Now, there's actually something else that's occurring here as a result of tides. So the picture that's being shown here is a exaggerated picture, but it's meant to illustrate a little bit more detail in terms of how exactly the tidal effect is taking place. So you got to remember that the Earth has this bulge because it's being pulled by the moon due to tides, but at the same time it rotates. So if you could sort of visualize the tidal bulge of the Earth, it would kind of look a little like this picture. Again, things are exaggerated here, but we say that the bulge for the Earth sort of leads the moon in its orbit. And the green arrow that you see there is meant to indicate the actual direction of gravity. Since the bulge that sticks out is closer to the moon is sort of more gravitationally attracted to that area of the Earth. Now we can break up that particular gravity direction into two other directions. One is directly pointed at the center of the Earth, and that's going to be the one that's responsible for keeping the moon in orbit. But there's another small force we can see here that points in the direction of the moon's orbit. And it's a force, right? So we learned in Newton's second law that forces cause accelerations. And so the effect here is causing the moon to accelerate in its orbit. Now, what happens when objects orbit, if they speed up in their orbits, how they compensate for that or how they adjust to that is by having a larger orbit. And this causes the moon to drift away from the Earth. It's not huge. It's measurable, though. The moon drifts away approximately a few centimeters every year. It's something that, like I said, we're able to measure because when the Apollo astronauts went to the moon, they left these things called corner reflectors on the surface of the moon, and that allows us to shoot radio waves at the moon and have them bounce off the mirrors and come back to the Earth, and we can time how long that takes, and then it gives us a very precise distance to the moon so we can see this steady drift in a way that the moon does. And that's going to have some interesting effects on the Earth in the future. Eclipses are one thing. The moon will not be able to eclipse the sun, but this is not going to happen for like a very long time, billions of years and things like that. In fact, the sun's most likely going to be gone before this becomes a major effect. Anyway, now, Newton's third law, right? If we're doing this to the moon must be doing something back on us. So there are kind of similar arrows, but they're all flipped, right? Opposite directions. And so there's a small arrow that points down on the Earth, which is opposite of the Earth's rotation. And that acts to slow the Earth's rotation down. Okay, now let's talk about Newton's second law again, right? The acceleration, or the rate at which things will change their speed, is a function of mass. And Earth is a lot more massive than the moon, so the effect on us is not as dramatic as it is on the moon. So yeah, we slow down, but it's like milliseconds per century. It's a very, very minor effect, but we've been around a long time. And we have seen from some very ancient geological records that the period of rotation of the Earth was a bit, the period was a bit shorter. The Earth had spun faster in the past, and now our day is approximately 24 hours, whereas in the past it was closer to maybe around 22. So that's an effect that occurs to us. All right. So this is, the tides explaining some effects that happen between the Earth and the Moon. And, these are all things that we're studying because we now know about the law of gravity and we know about the laws of motion. So that's kind of a neat application of taking all those principles that you just learned and applying them to explain something that's going on in space. All right, so now we want to turn our attention to talking about seasons, okay? One of the reasons we're doing this is because we've talked about the celestial sphere before, and we have talked about this concept of the ecliptic, which is the path that the sun appears to take as the Earth orbits the sun. And we haven't exactly connected the two together. Like, where on the ecliptic would you find where on the celestial sphere would you find the ecliptic? So we're going to go about doing that by talking about seasons. Seasons are going to allow us to visualize both these things, and then we can kind of put them all together. So I kind of want to remind you about some things we talked about with regards to the celestial sphere. So you might remember this picture from a previous lecture. It's a cross-section of the celestial sphere. The line that's drawn, the semicircle here, is the meridian. That's sort of split in the sky into east and west. We're sort of facing west here. We have a north to the right and south to the left. It's just a cross-section of the celestial sphere to help us, try to visualize something that's 3 dimensions into 2 dimensions. And we have our north celestial pole here, which lies above the northern horizon. And the celestial equator here, which is CE, remember that's a line. It's the projection of Earth's equator into the sky, and it's a line that goes from east to west, and it crosses the meridian at a location that is down from zenith. And in fact, the position of the north celestial pole and the celestial equator are a function of an observer's latitude. Right? North celestial pole lies above the horizon by an angle that's equal to your latitude, and where the celestial equator crosses the meridian is going to be your latitude down from zenith. All right. So we have these two systems here. Both these systems are what are called orthogonal systems. That's a fancy way to say perpendicular to each other. So the celestial equator and north celestial pole, that's centered on how things on the Earth, whereas zenith and horizon are centered on how the observer sees things. So I just wanted to remind you about these two things because we're going to be talking about them later in the lecture today. All right, so seasons, right? When you think of seasons, right, you want to think about some of the observable things that you associate with the seasons, because we're going to try to explain some of those things. When you think about seasonal effects, there are sort of 3 main things that you can attribute to the seasons. 3 distinct and important things that are seasonal effects. The most obvious one is temperature, right? It gets hotter in the summer, it gets colder in the winter. So that's something we're going to want to try to explain. Another thing we want to explain is you might have noticed that periods of daylight change throughout the year. If it's summertime, there tends to be more daylight and less nighttime. So we want to aim to explain that. There's a third effect that may not be as recognizable or noticeable. You might have seen this before, but the position of the sun in the sky varies over the course of the season. So, like when it's summertime, the sun tends to rise further north of east and kind of gets more overhead around noon and then sets further north of west. And in the wintertime, it tends to be further south, right? It rises more southeast, doesn't get very high up in the sky, sets kind of southwest. All right, so these three things, we want to explain this stuff. Why is this happening here? Now, I'm showing you this picture here to dispel a potential myth that you might have about seasons. And it's a very common myth with regards to seasons. And it's a very almost understandable assumption that people make about seasons. The myth is that seasons are caused because the Earth is closer to the sun or farther away from the sun. And that's not true, right? So this is an ellipse that I have here, and it's exaggerated. I mean, if you remember, the ellipse for Earth's orbit is, basically circular. So I had to draw an exaggerated one just to kind of highlight what we're talking about here. But perihelion, where we are the closest to the sun, occurs in January, which is winter for us in the northern hemisphere. And when we are the farthest from the sun, that's aphelion, and that occurs in early July, right? So this seems backwards. If you are expecting us to be closer to the sun in summer, this does not appear to be true. It's the opposite, actually. Obviously being closer or farther from the sun would play a role in things being hotter or cooler. But it's actually a pretty minor effect. In fact, there's another thing you can point out that kind of demonstrates that this is not how seasons work, is that seasons are switched in the hemispheres. So if it's summer in the northern hemisphere, it's actually winter on the opposite side. Okay, so that wouldn't make sense if distance was the reason why these things are occurring. So what is occurring here? Well, it's not about how close the Earth is from the sun. It's more to do with how sunlight hits the Earth at different parts of its orbit. So, as Earth orbits the sun, it also rotates on its axis. The rotational axis is tilted for the Earth. There's a 23.5 degree tilt of the Earth's axis from something that's vertical, right? And that tilt is the reason why all the seasonal effects occur. You can see in the picture, and the most obvious thing that you're seeing in this picture is that the northern latitudes are getting mostly direct sunlight, right? The sunlight is hidden almost directly overhead, whereas you look at similar latitudes in the southern hemisphere, that light appears to be spread out. It kind of hits at an angle, and it's spread over a larger area. So you're just getting less light per unit area there. And that is, the main reason why there are temperature differences for the seasons, because the northern hemisphere is not only receiving more direct sunlight, but if you notice in the picture here, more of the northern hemisphere is just in sunlight. And the way that weather patterns work, heat will get trapped in the northern hemisphere, and then over the course of the months of the season kind of builds up. So, and then the southern hemisphere, the opposite's true. The sunlight does not hit directly, and there's less of the southern hemisphere actually in the daylight there. So that's a big effect, right? And that's going to be largely why temperatures are going to be higher, right, in the summertime. A few other things going on here. You see these latitude lines drawn, right? And if you look at the 40-degree north latitude line, you'll notice that more of that line is in daylight and less of it's in darkness. So, as the Earth rotates and somebody's at this latitude, that's kind of, where they're going to be as the Earth rotates on its axis. And you can see that we're spending more time in daylight, less time in darkness. Okay, if you look to the south here, the 40-degree south latitude line, We see the opposites. There's more of the lines in darkness and less is in daylight, right? So that's the reason for why we have these different periods of daylight, but it does also contribute to the temperatures, right? Because if the sun is up for longer, that means more light's going to be hitting the earth in those areas, and now obviously that's going to create a higher temperature. You might be familiar with the idea that at the extreme latitudes of the earth, very close to the poles, that you can have situations where sunlight can persist for weeks or months. Sun doesn't actually set or rise in particular areas. And this figure kind of nicely illustrates how that's happening. If you're really close to the poles, imagine, latitude lines that are like 70 or 80 or, all the way up to 90 are going to be very close to the pole up here. And those lines are going to be perpetually in daylight, during that time. In fact, due to the tilt of the Earth, some of those latitudes get tilted into permanent daylight. And so the sun can stay up for weeks at a time, right? And then the opposite's occurring down the southern hemisphere here. There are certain latitude lines you can imagine that just never get to the daylight part of the Earth. So the sun sets at some point in the year and just stays down for weeks or months. So that kind of explains that. Let's look at this other picture here. So this is kind of contrast in two different positions of the Earth in its orbit. Now the picture on the left is what you've been looking at, but the picture on the right would be about 6 months later. So the Earth moves in its orbit to the other side of the sun. The direction of the tilt's not changing over the course of the year here. So now for the northern hemisphere, you're tilted away. And this is going to be winter time, but now it's summer in the southern hemisphere because they're receiving more of the sunlight. So we can see why the seasons are flipped, because one hemisphere is always tilted toward and one hemisphere is always tilted away. It just depends on where the Earth is. Now, if you had to see a picture of like fall or spring, the tilt is not either toward or away. The sun is sort of perpendicular, so to speak, to the tilt, so that sunlight kind of hits latitudes evenly, and so you don't get anything that's too incredibly hot or too incredibly cold. That's how that would sort of go. Now, another thing that's good about this picture, it kind of illustrates why the sun's position in the sky is going to change. So if you look here, for latitudes that are maybe between like 20 and 25, sunlight is hidden directly on those latitudes in the northern hemisphere. So the sun is pretty much directly overhead, close to zenith, right? But then when the Earth has moved 6 months later, those same latitudes, they don't get direct sunlight. In fact, you can see the equator here. If you extend that line out, that's the celestial equator. We see that the sun's position in the sky is below the celestial equator, whereas on the picture on the left, it's above the celestial equator. You see the equator here? That line would extend down and to the right, and so the sun's position is above it, but here the sun's position is below it. So over the course of the year, it can vary above and below the celestial equator, and the variation is the Earth's tilt, 23.5 degrees above and 23.5 degrees below. All right, so let's try to visualize that from another perspective. Here is a more of a celestial sphere perspective on what's happening here. So summer's on the left and winter's on the right. And again, you can see that because we're going to be tilted toward the sun in the summertime, that the sun will be further north of the celestial equator. So it will travel on an arc that is parallel to the celestial equator, but further up. So it's further north when it rises and further north when it sets, and it's more overhead when it's noon. And then you can see the one for winter when we are sort of tilted away because we've moved to a portion of our orbit where that occurs. Then the sun is just further down in the sky. Right, so it rises further south and sets further south, and it tends to be farther down in the sky. And they kind of show in the picture like an illustration of how shadows might look. Right, if we're talking about noon, this person has a very short shadow because the light's almost directly overhead, and that's kind of showing this flashlight picture down here. The light's kind of coming almost straight down. That's more concentrated sunlight. whereas the sun's at a pretty steep angle when in the wintertime, and it's like the picture that are shown in the bottom right here, and that light is basically spread out over a larger area, and that's less light per unit area, so that's obviously going to have a really big effect. I do want to try to illustrate this with the Stellarium program. I have shown you this program before in a previous video lecture. This is sky simulation software. It allows you to choose any location, any date and time, and then you can get a sense of what the sky looks like, and you can simulate movement and things like that. And right now we have this set up so that we're in Lancaster. I'm currently facing south. It is noon on one of the days in early September. I turn the atmosphere off so that you can more easily see what's going on with the sun. There are a few lines up here that you can see. We have the celestial equator here. That's the magenta line that's going across the screen. Remember, that's the line that goes from east to west, and it crosses the meridian, which is the red line here, down from zenith, an angle that is equal to your latitude. You hopefully remember that from chapter 2. At the very top is zenith here. You can see the lines that run parallel to the horizon. These are lines of altitude. The first one above the horizon is 10 degrees, then 20, 30, all the way to you get up to the zenith, which is 90 degrees. So if you actually go down from zenith, right, we have one line here that's 10 degrees, then 20, then 30, and then the equator is halfway between the 30 and 40 line. Our latitude is 35 degrees. So the position of the celestial equator is 35 degrees south of zenith. Great. You can see where the sun is positioned at the moment here. It is a little bit above the celestial equator. When the sun rose on this day, it was a little more north of east. At noontime here, it's a little bit above the equator. We say that's a little bit north of the celestial equator. And then when it sets, it's going to be a little bit more north. And that's how it's going to look for the entire day. Now, what I'm going to do here is I'm going to leave the time at noon. And then I'm going to go forward in days. So I have a button here that just advances the days without changing the actual time of day. And what you'll notice here is I'm going to go ahead and start clicking ahead here. So we see the position of our sun starts to drift a little bit closer to the celestial equator. And right at this point, it seems to hit the celestial equator. And I look down there at the date, and it says September 22nd. As you might know, that's a date that's pretty close to the autumnal equinox, better known as the first day of fall. So that's where the sun is positioned. So it's going to rise exactly east and then stay on that line the entire day and set exactly west. I'm going to continue the days, and we see that the sun is now drifting further down with respect to the celestial equator. That's going to keep happening. It gets further and further down. Remember, this is noon, so the sun is getting pretty low in the sky, and it reaches kind of an extreme position right around here or so. This is, according to the date, around December 23rd. This is close to the first day of winter. The position of the sun gets the furthest south or below the celestial equator. So it's going to rise very south of east and transit very low in the sky. Then it's going to set very south of west. And then as I progress through the season of winter, we see our sun's going to go back and hit the celestial equator. This is March 20th. That's going to be the first day of spring. This is the season of spring as it drifts higher up in the sky, reaches a maximum position right about maybe there or so, and that's showing June 22nd, first day of summer or thereabouts. And this is the cycle that the sun goes through over the course of the year. It gets further up in the sky, it gets further down in the sky, and this is all due to tilt of the Earth, where we are in our orbit, and it changes how the sun appears in the sky. It can be further up, at times or further down. This really defines what the seasons are. It has to do with where we are precisely in our orbit to cause the sun to be in these different positions of the sky. So we go back to our slides here. So this is a picture that attempts to put the celestial equator and the ecliptic together. So this is a kind of a unique celestial sphere perspective. They are showing the Earth as having a tilt. The ecliptic is a horizontal line here, and we can see the celestial equator is tilted 23.5 degrees. And the dashed line you want to imagine is, how the sun appears to shift as we orbit it, right? So now in astronomy, the year starts at what we call the vernal equinox. It's the first day of spring. The vernal equinox is not only a date, the first day of spring, which occurs around March 19 or 20, but it's also a location in our orbit. And it's the location where the tilt of the Earth is not necessarily toward the sun or away from the sun, it's kind of on the side, so we get evenly hit with sunlight. And when you look for the sun, it is directly on the celestial equator. So it's going to rise east, transit right on the celestial equator, set exactly west. And you might notice this, if you live in the Alp Valley, you've seen this effect actually, because the way we have streets built in the Alp Valley is everything's a grid, right? North, south, east, west. So when it gets close to this first day of, say, spring or something, if you're driving in the early morning and you're going east, you got the sun just right there in your face, right? Because you're just going directly east. And then if it's later in the day and the sun's setting and you're going west, again, right in your face. So there's like this couple weeks or so of time, like around the first day of spring and autumn, where we just get this horrible driving conditions because the way they build the streets, but it only occurs then because the sun's position is going to change in the sky as we move around our orbit. Right. Okay. So the season of spring is really defined by this particular spot in our orbit, and it continues until the sun appears the furthest above the celestial equator that it's going to be, which is 23.5 degrees, and that's the summer solstice. And you can see the dates here on the side for when this stuff occurs. Summer is defined as the amount of time it takes to go from that location to the autumnal equinox, where we are once again have the sun kind of to the side. Relative to the tilt, and the sun is exactly on the celestial equator there. Then fall is progressing as the sun gets further down to the first day of winter. Winter solstice is when the sun gets the furthest down. So this picture is kind of explaining the definition of the seasons. It's all due to Earth's orbital position, and that orbital position is going to determine how sunlight's hitting the Earth. That's why if you look up, any of the equinoxes of the solstices, like when they occur, they tell you down to the second when it occurs. It's not just the day. It's down to a particular second where it's that exact spot where we reached the position in our orbit. Okay. So that's our means to do that. Now we can go back to our original picture of our celestial sphere, and we can add in some extra information. So, we have our celestial equator there. We have the North Celestial Pole. That's based on our latitude. Great. And now we can throw in the solstices and the equinoxes. Right? The equinoxes are aligned with the celestial equator. And summer solstice is 23.5 degrees above. And the winter solstice is 23.5 degrees below. And the sun will be found somewhere in between those two green lines. Okay. And this picture is for Lancaster. So, you notice the sun never gets to the northern part of the sky. It always stays in the southern part of the sky. It doesn't quite get overhead. It gets close. And it can get pretty far down, as you see. So if it's the first day of summer, you're going to find the sun, hitting the meridian right up the top there. And then throughout summer, it's going to start to drift down until you get to the first day of fall. That's when it gets to the celestial equator and so on. Okay, great. Let's talk about some questions to see if you have followed what I've been describing here. Does the sun ever get directly overhead for an observer in Lancaster? Think about this for a minute. Do you remember the term directly overhead? What does that mean? That means zenith, right? All right, so the answer here is D. It never does. Never does. Gets close, right? Go back to the picture here. So you can see that the summer solstice is not quite at zenith. It gets close. The angle between celestial equator and zenith is 34.7 degrees, and the Earth's tilt is 23.5. That's a difference of about 11.2. So this small little angle right here between summer solstice and zenith, 11.2 degrees. So it does get close, pretty close actually, but it doesn't technically get directly overhead. But you know what? Being like 11 degrees off is a lot of light still. You can do some math to talk about the amount of light that hits, but when the sun is at summer solstice, we are getting something like 98% of the full sunlight that we could get. So that's quite a bit. So the fact that it doesn't get directly overhead doesn't matter too much. It can still get pretty hot, and if you live in the Elm Valley, you know it definitely gets pretty hot. Where on Earth do you need to place yourself in order for the sun to appear directly overhead? So it doesn't get overhead, right, in Lancaster. But you can go to another latitude, right? So where do you think you have to go? The answer here is B. So you got to walk further south, right? If you walk further south, your latitude goes down, and then your celestial equator can start to drift further up in the sky. If I go back to the picture here, that whole system that you see with the green lines and stuff, that shifts closer towards zenith. And if you actually go 11.2 degrees further south, then it means the summer solstice will be aligned with zenith, right? And there's actually a special latitude called the Tropic of Cancer. There's a similar one called the Tropic of Capricorn that exists in the southern hemisphere. And the significance of these two lines is that if you are within these two latitudes of the equator, then the sun will get directly overhead for you at some point. But for the Tropic of Cancer, that some point is the first day of summer, and for the Tropic of Capricorn, that would be the first day of what we would call winter in the northern hemisphere. Obviously, in the southern hemisphere, they're going to call that summer. So you can get it directly overhead, but you got to be close to the equator for that to occur. All right, last question here, a little bit more challenging. On the winter solstice, where does an observer have to be located in order for them to place the sun directly overhead? All right, think about that for a moment. And the answer is C. Okay, the winter solstice would be on zenith if you went past the equator and you went all the way down to 23.5 degrees south. So again, go back to the picture. So if you actually went south, you crossed the equator, and you were going down to that latitude line, this whole system that's on the left-hand side would then shift over to the right-hand side. And the winter solstice line would line up with zenith. And then the sun would be directly overhead on the first day of winter for the northern hemisphere. But again, like I said, they would call it summer in the southern hemisphere. All right. Great. Now, one last thing I want to talk about before we wrap up this video, and it's something I have discussed in a previous lecture. It's the effect of precession. And this was brought up back in chapter 2 because precession is an effect that changes the direction of the Earth's axis of rotation. Doesn't change the amount of tilt, but it does change the direction of the tilt. And the reason that was important for us earlier is because it caused different things in the sky to become the pole stars. Right now, we're pointed at Polaris. 5,000 years ago, we were pointed at a star called Thuban. So that shifts over time, and that's the reason I brought it up. Now, precession is kind of slow. I mean, a precessional period is 26,000 years. Now, I have a video stated at the bottom here, and I'll have a link in the description, but it's the same video that I had mentioned back in chapter 2. So you might have already seen it, but it kind of demonstrates, what precession looks like. They use like a top and a special device to illustrate it. Now, why am I mentioning this here? Well, if precession changes the direction of the Earth's tilt, that's going to mess with seasons, right? It's going to mess with the seasons. So I have this last question here. What effect on the Earth, if any, is produced by changing the direction of Earth's axis of rotation? So look through these and think about them. And what do you think is going to be different here? The answer here is C. It's going to shift when seasons occur. Okay, because again, if we're tilted toward the sun and it's summertime, and precession is going to shift that, half of the precessional period is 13,000 years, and 13,000 years from now, in that same position, we're not tilted toward the sun. We're going to be tilted away from the sun, and it actually would be winter time during the months of June, July, and August. So yeah, the calendar dates of the seasons change. And you may be wondering, well, how dramatic of an effect is that? Well, if you take 26,000 years and you divide them by how many days there are in the calendar, 365, you get a number that's around like 71 or 72. Let's just go with 72. That means every 72 years the seasons shift and they're off by 1 day. And I believe they occur earlier. They're going to be earlier by 1 day. And that's what the effect is. So over the course of your lifetime, you won't really notice this, but we have noticed over, by studying ancient records of things that seasons occur. It appears to be at different times because of this. In fact, these other things that are on here, let's talk about those because a lot about how the solar system works now, and we can actually go through all of these and kind of ask ourselves, why these things occur. So let's talk about this. The length of the day changes. Length of the day changes, right? We have a sidereal day, 23 hours, 56 minutes, 4 seconds. And then we have the solar day, it's 24 hours, right? Why is that occurring? It's Earth's rotation. If you want to change how long the day is, you just got to change Earth's rotation, speed it up or slow it down. Okay, great. The length of the year changes. Okay, think about how you would do that. Now, you might think, because of us talking about you just got to speed up the Earth in its orbit or slow it down in its orbit. Well, no, actually. Remember Kepler's third law, right? The amount of time it takes to orbit the sun is directly related to distance. Turns out that if you try to make the Earth go faster in its orbit, and you keep it at 1 AU, it's just going to slow back down. Okay, if you slow it down, it's just going to speed back up. So there's really, how the amount of time it takes to orbit is locked in by the distance. So if you want to change the length of the year, you actually have to change the distance that the Earth is from the sun. That's how you're going to do that. We already talked about calendar dates of the seasons changing, length of the season changing. What do you think does that? Well, when I ask this question to students, probably the number one response I get is, change the tilt. Make the tilt more, make the tilt less. No, that actually doesn't do that. Changing the tilt of the Earth is going to change the severity of the seasons. If you make the tilt greater, then everything that we've discussed in this video is going to be more extreme. And if it's less of a tilt, then it's a weaker seasonal effects. And if there's no tilt, there's no seasons, which on the surface sounds pretty nice because I like spring, fall's okay, but you kind of kill the biodiversity on the Earth. A lot of things kind of depend on that cycle of the seasons, right? So anyway, changing the tilt, no, not going to do it. But ask yourself this. How long are seasons? Well, about 3 months. Well, why are they 3 months? It's because 12 months divided by 4 seasons is 3. So if you're going to change the length of the seasons, guess what you got to do? You got to do the same thing you did in part B. You got to change the year. Okay? You look at, for example, like Mars. Mars has a tilt that's really close to the Earth's tilt. It's like 25 degrees or something like that. It's very close. So it has seasons like we do. But the orbital period of Mars is something like 2.25 years. So seasons on Mars don't last 3 months. They last more like almost 7 months, just because of the longer orbital period. So that's kind of neat. And then we got the last effect here. No effect at all. How do you do that? Well, you just sit and you watch your favorite movie. How about that? And there's no effect in the Earth other than you being happier because you're watching a movie you probably like a lot, or I don't know. Anyway, there's a lot of ways to do nothing. But you didn't do nothing. You just watched this video. So congratulations on getting through the video. And the next video is going to be on the moon, and I will see you there.